Que atleta! Tem que ser atleta. É tudo uma correria só.
Senta aí. E se quiser botar o celular junto, quem vai conseguir os mensagens na internet. Aí eu vou esperar um pouquinho, porque está atrasando.
O elevador só desce, não sobe.
Ah, é? É. Ai, meu Deus. Se você botar aqui, pede a frequência, é fácil. Juliana, está emissão?
É assim,
9 horas.
eu não sei se temos que falar por alguns participantes aqui.
É? Mas sim, dá um tempo, vai de duração de flash. É.
Ok, pronto.
Então, so good morning, everyone. Yes, you are all online. I'm Nadia. I'm from with the University of Rio de Janeiro. I'm going to chair this session with Luisa, also from the University of the Rio de Janeiro. I'm going to ask if the presenters are online, are ready. So you have Lunek. Are you there? Yes.
Hello, my name is Asrani.
Okay, Asrani is the second paper, and there is Vinicius Thiago. Is there? No? For 10 o'clock, and Cristiano. Also, seems there's a little bit, but they are from 10:20. There is Flavia Tellis as well. So Flash is not here as well. So we have the first and the second speaker. Now, I'm going to call on Luneki to present his paper, The Scaling for Area Coverage in Swarm Robotics. So, Luneki, you have 15 minutes to get on with your presentation. You have the floor now. Thank you.
Okay, thank you. Can you hear me?
Yes.
Okay, I will start my presentation. Good morning. It's my pleasure to present our work entitled Rescaling for Area Coverage in Swarm Robotics, developed in collaboration with Nadia Nedja and Luisa Morelli at the University of Rio de Janeiro, Brazil. This work investigates how a swarm of autonomous robots can collectively adapt its spatial distribution to efficiently cover areas of different sizes. This presentation is organized into 6 parts. First, I will briefly introduce the field of swarm robotics. Then I will explain the concept of message waves, which provide the communication mechanism for our methodology. And after that, I will describe the rescaling strategy for area coverage. Finally, I will discuss the simulation results and conclude with the main findings and future work. Swarm robotics is a research field that studies how a large number of relatively simple robots can cooperate to perform complex tasks through local interactions. The inspiration comes from natural systems such as ant colonies and bee swarms, and in these systems, there is usually no central controller. Instead, complex collective behavior emerges from simple rules followed by each individual. This decentralized approach provides 3 main advantages. It increases robustness, flexibility, and scalability. To implement collective behaviors, we model the swarm as a communication network composed of distributed processing nodes. In this network, each robot acts as an autonomous computational unit that can exchange information with its neighbors. Rather than rely on a central controller, the swarm operates as a distributed processing system where global behavior emerges from local interactions. In this work, we focus on a particular class of distributed algorithms known as message wave algorithms. These algorithms provide a genetic framework for coordinating the swarm and can be used as building blocks for implementing a wide variety of collective tasks. Our approach is inspired by information propagation with feedback algorithm proposed for distributed networks. The process begins with an initiating robot that spontaneously sends a message to all of its neighbors. Each robot can receive the message for the first time propagate it to its own neighbors. Eventually, every robot receives the message wave. Once a robot has completed the propagation process and has received the responses from all of its neighboring robots, it sends a feedback message to the robot from which it first received the wave. This feedback mechanism propagates back toward the initiator, and when the initiating robot has collected feedback from all of its neighbors, it can guarantee that the entire swarm has participated in the process and can safely perform a decision event or start the next collective task. This slide illustrates how the message wave algorithm guarantee termination, and the process starts with the initiating robot, Ray, with broadcasts the initial message. As the wave propagates to the swarm, a temporary hierarchical structure is established, and each robot identifies the neighbor from which it first received the message as its parent, while the robots that receive the message from it become its children. The messages flowing from parents to children are called propagating messages. After completing their local operations and receiving responses from all of their own children, robots send feedback message back to their parents. In swarm robotics, collective tasks are operations that emerge from the coordinated actions of many individual robots rather than from the behavior of a single agent. Our message wave methodology provides a unified framework for developing such behaviors. Using the same communication mechanism, we have implemented several collective tasks, including recruitment, alignment, navigation, aggregation, and dispersion. This demonstrates that message waves can serve as a common building block for a wide range of swarm robotics applications. Swarm resizing is a collective behavior in which robots adjust their relative positions in order to control the overall spatial extent of the swarm. Each robot moves with respect to its neighbors so that the group can neither contract or expand. This behavior is characterized by a resizing factor, defined as the ratio between the final and initial inter-robot distances. This parameter directly determines the global effect of the local motion rules. When the resizing factor is between 0 and 1, the swarm performs aggregation, meaning that the robots progressively reduce their mutual distances, resulting in a more compact formation. Conversely, when the resizing factor is greater than 1, the swarm executes dispersion, increasing inter-robot distances and expanding the covered area. The movement of the swarm during resizing is inspired by classical flocking models. In flocking systems, the motion of each agent is governed by three fundamental rules: separation, alignment, and cohesion. These rules collectively ensure that agents avoid collisions, maintain a common direction, and stay grouped. In our approach, we extend this model by incorporating an additional rule set. The speed of each robot is determined by four components: cohesion, separation, parent tracking, and collision avoidance. During movement through the environment, the swarm must preserve connectivity while navigating. To achieve this, we combine cohesion and separation rules to ensure that robots remain with communication range while avoiding excessive crowding. The figures show how to obtain the distance for cohesion from the distance between the robot and its neighbors, and the distance between its neighbors and the limit of the robot's perception, so that the swarm may maintain its structure and as it progresses through the environment. In addition to maintaining connectivity, the swarm must also ensure safe navigation without losing any robots during displacement. For this purpose, we incorporate parent robots tracking together with obstacle avoidance mechanisms. Parent tracking ensures that each robot maintains a reference within the message wave hierarchy, while obstacle avoidance prevents collisions with the environment. The final motion of each robot is obtained by combining the keys of the four behavior rules: cohesion, separation, parent tracking, and collision avoidance. This combination is implemented as a linear weighted sum where the resulting clockwise and counterclockwise motor velocities are computed from the contributions of each rule. To evaluate the proposed approach, we conducted a set of experiments using VREP simulation environments, which provides a realistic platform for testing multi-robot systems. The simulated swarm is based on a model of kilobot robots, a widely used platform in swarm robotics research. This model captures the essential capabilities required in our experiments, including message exchange, as well as sensing of distance and relative position between neighboring robots. Each robot is therefore able to interact locally with its neighbors through communication and sensing, enabling the implementation of the message wave-based coordination strategies presented in this work. We evaluate the performance of the proposed swarm resizing mechanism through both aggregation and dispersion scenarios. For aggregation, we consider swarm ranging from 2 to 25 robots and test different values of the resizing factor. The main performance metric is the convergence time of the aggregation process. For dispersion experiments, we use the same swarm sizes but with resizing factors greater than 1. In this case, we evaluate the time required for the swarm to expand to the desired configuration. To better understand the dynamics of the message wave process, we introduce the concept of critical path in a swarm. A critical path is defined as a sequence of robots starting from the initiator and ending at a leaf robot. In these words, it presents the longest chain of parent-child dependencies in the swarm. This path captures the most time-consuming propagation route of the message wave process and therefore provides an important indicator of the system performance. By this video, we present a simulation example of the aggregation process for a swarm of 25 robots with a resizing factor of 0.8 executed over 10 iterations. It shows how the robots progressively reduce their mutual distances while maintaining connectivity through local interactions. Starting from a initially dispersed configuration, the swarm gradually converges toward a compact formation. Now we present the results obtained for aggregation scenario in terms of the convergence time. The first plot shows how the aggregation time varies with the size of the swarm, ranging from 2 to 25 robots, from different values of the resizing factor. In general, we observe that the convergence time increases as the number of robots grows, which is expected due to higher communication and coordination complexity in larger swarms. We also observe the clear influence of the resizing factor on the performance. Large values of resizing factor, which correspond to milder aggregation, tend to result in faster convergence. The second plot summarizes the average aggregation time as a function of the critical path size. The results confirm a strong correlation between a dip of the communication structure and the execution time. Going forward, we present a simulation example of the dispersion process for a swarm of 25 robots using a resizing factor of 1.4 executed over 10 iterations. The video illustrates how the swarm expands its spatial configuration in a coordinated and decentralized manner. Starting from a relative compact formation, the robots progressively increase their inter-robot distances while preserving connectivity and maintaining the structural integrity of the swarm. Now we present the quantitative results obtained for the dispersion experiments in terms of the execution time. The first plot shows how the dispersion time varies with swarm size for different values of the resizing factor, ranging from 1.2 to 2.0. In general, we observe the execution time increases with both the number of robots and the value of resizing factor. This reflects the fact that stronger dispersion requires larger relative movements and more coordinating among robots. And the second plot presents the average dispersion time as a function of the critical path size. The results indicate a clear correlation between the dip of the message wave trajectory and the overall execution time, confirming the importance of the underlying communication topology in the performance of the system. In this work, we proposed a message propagation based strategy for implementing collective tasks in swarm robotics. Experimental results demonstrate that the proposed message wave framework is sufficiently general to support different types of collective behavior, including aggregation, dispersion, and navigation-related tasks. A key advantage of the approach is that message waves inherently provide a mechanism for termination detection, allowing the initiator robot to determine when the entire swarm has completed a given task. Several directions for future work can be identified, and we plan to further investigate the behavior of the implemented tasks under more diverse and previously unexplored conditions, including different swarms, densities, and spatial configuration. This concludes the presentation, so thank you very much for your attention e obrigado a todos.
Thank you, Ned, for your presentation. Nice presentation. Any questions? Well, any question for the online presenters, for the online? No, doesn't seem so. I don't have any question. Do you?
No.
No? So, Ned, thank you very much. I'm going to give 5 minutes for Flavia. Flavia is there? Flavia, yes, Flavia is there.
I'm here.
Okay, I'm going to give some, yes, hello. We're going to give some 5 minutes to start the next presentation, okay?
Okay.
All right. Flavia, you can share your presentation. It's 9:20. Okay, we can start. It's 9:20. Yes, we can start. Flavia, you have the floor. So Flavia is going to present breast nodule detection and classification using convolutional neural network with transfer learning. So you have 15 minutes to show us your work. Flavia, you have the floor.
Okay, thank you. Good morning, everyone. Thank you all for coming. My name is Flavia Teles, and I'm a student in the postgraduate program at the State University of Rio de Janeiro. And I would like to present our study on breast nodule detection and classification using convolutional neural networks with transfer learning. Let me give you a brief overview of how I'm going to organize this talk. I've divided the presentation into 5 parts. First, I'm going to give some cancer background. Then I'm going to explain the neural networks we used. After that, I'm going to talk about the data and infrastructure. Next, I'm going to show the results we obtained. And finally, I'm going to present the conclusions and some directions for future works. Let's begin with a quickly cancer background. Cancer is not a single disease. As you know, it's a group of more than 100 malignant diseases, each one with its own disorder growth. It is also the second lead cause of death in the world. And when we look at Brazil, the scenario isn't different. Looking specifically at breast cancer, the picture on the right, but in the first incidence place in women number. And I would like to draw your attention to one important detail: time. The stage at which diagnosis takes place a lot between cure and fatality. As you can see in this chart, the 5-year survival rate is around 99% when the disease is found at an early age. For advanced case with metastasis, it drops to only 20%. In other words, the earlier we detect, the higher the chance of cure. However, diagnosis depends entirely on human visual accuracy, which could be affected not only by technical issues like dense breasts or noise in the image, but also the fatigue and experience of each professional. So we propose 2 approaches to improve this diagnosis. The first is focused on detection, the UNIT architecture with semantic segmentation. It answers one question: where is the lesion? The second is focused on classification using the VGG6 architecture with learning. And it answers a different question: what is the lesion? We want to understand whether it is really necessary to delineate the exact area of the lesion before a user diagnose, or the global reading of the image is not enough and more robust. Now I would like to explain a little bit about neural networks. Beginning of the base of everything, the convolutional neural network, or CNN. A traditional neural network flattens the image into a line of numbers. When it does that, it loses the spatial structure, that is, the relation between neighboring. The CNN works in a different way. It proceeds for information locally with convolutional layers that slide small filters over the image. With this, the network extracts features in a hierarchical way. It starts with simple edges and textures, and then it builds more complex patterns. The pooling layers reduce the dimensions and give some resistance to small movements in the image. At the end, the fully connected layers produce the probability for each class. Looking at the UNet, which we used for segmentation, we see a symmetric shape. On the left, the encoder is a contraction path that captures the context, reducing the resolution with max pooling. On the right, the decoder is expansion path that covers the resolution and gives precise localization. The strong point here is the skip connections, the horizontal arrows that link the feature map from the encoder directly to the decoder in order to preserve the high resolution information, which is essential to define the exact edge tumor. Now I'd like to look at the VGG16 that belongs to VGGNet family, and it's a strong feature extractor. Its main characteristic is the use of sequential convolutional blocks with small filters of 3 by 3 pixels and a stride of 1 pixel. The design lets us increase the depth of network while keeping the number of parameters under control. The images pass through 5 convolutional blocks, going from 224 by 224 down to 7 by 7, and then through the fully connected layers that produce the final classification. So I would like to show a way to accelerate the VGG16 training, transfer learning. Instead of training the network from scratch, we started from waves that were already adjusted on ImageNet's dataset, a very large set of natural images. The network already knows how to recognize general features like edge, shape, and textures. We use this knowledge and adapt only the final layers to our specific task, the mammograms. The benefit is clear. The model reaches convergence faster and needs less data than a full training. To conclude this section, a brief overview about metrics. As we have to approach segmentation and classification, it was necessary different metrics to evaluate them, as you can see in this slide, and I'm going to explain a little bit more in results. Let's now to move on to data and infrastructure. The database used is the CBIS DDSM, the curated breast image set of DDSM. Is a curated version validated by specialists, and it provides icon images together with a clinical metadata. We made one important choice here. We kept only the masses, the case annotated as massive, and we discarded the calcifications. The reason is the segmentation task. Masses tend to have more cohesive shape with borders that are reasonably well-defined. Calcifications are different. They appear as small points scattered across the tissues. This would make the segmentation with UNets even harder if you choose to discard them. For the mass type, the subset has around 1,000 mammograms images. Considering this number, to compensate this and increase the variability of data, we applied data augmentation. The data loader applied random transformations during the training. As you can see, from a single sample, we generate many versions: rotated images, change in brightness and contrast, mirrored image with zoom and shear. The network sees a different versions at each epoch. This helps the model to generalize better and reducing overfitting. Besides remove the barrier of local hardware and guarantee the reproducible and scalable, we choose Google Collaboratory Platform with an NVIDIA T4 GPU. The framework was PyTorch, and we use libraries like Python, Pandas, TV. And to give you an idea of the cost, training with the VGG16 was not heavy. On a stable app, the cost was about 1.3 seconds per image for one app. So the T4 was enough to train the model in a reasonable time. So let's analyze the results we obtained. Starting with the UNet, we ran 4 experiments. What we changed between these experiments were a few key factors. The experiment number 1, we used the original dataset with no data augmentation. In experiment 2, we added data augmentation. In experiment 3, we reduced the learning rate by 10 times to see if a slower learning would help. In experiment number 4, we trained longer, 50 epochs, and used a hybrid loss, DICE plus BCE. Look at the results closely. Well, the best DICE was around 0.64, and the best IOU around 0.49. The difference between the two is that DICE gives more weight to the overlap, while IOU is stricter. Both values are low in our results. And if you already read the classification side to check if a detection network could help the diagnosis, these pictures are also weak. The accuracy stayed at 55%, and the recall reached at most 60%. These low and flat numbers point to underfitting. Due to these limits, we moved to second phase, the classification with VGG16. One more time, 4 experiments. Starting use the UNet, starting use the network as a fixed extractor after introducing the fine tuning and freezing block 5 and learning rate schedule. The third dropout rate to 0.7 and data augmentation, and finally at 4 class balancing. In the first experiment, if you look at the accuracy graph, the training accuracy rises consistently above 80%, but the validation accuracy stops early. This is a clear signal of overfitting. The model memorized the training data, but did not generalize. In the confusion matrix, what really matters here is the malignant row. The model produces high volume of false positives, so the precision dropped to 53%. The sensitive was 65, but the model was still memorizing, not learning. In the second experiment, we tried fine tuning to give the model more capacity. But without proper compensation, this made the model unstable. The training accuracy went above 90%, and the training loss went almost 0, while the validation loss became volatile with high peaks. The result was the worst of the phase. The sensitivity dropped to 54%. Look at the confusion matrix. The model failed to identify almost half of the malignant cases. So a more powerful model alone was actually worse because it sent many sick patients home. To control this instability, we moved to the third experiment, where we implement a strong regularization strategy. We kept the fine tuning, but we raised the dropout rate to an extreme value of 0.7. This forced the network to be less dependent on specific neurons and effectively established the training process. In the fourth and final experiment, we tested whether class balancing through wave sampling could further improve the system. We forced the data loader to select samples from the minority class more frequently. However, both experiments converged to the exact same performance. As you can see in the matrix in the right side, the combined approach established our results. We achieved an overall accuracy of 65.3%, and more importantly, a sensitivity of 66%. In clinical terms, these matrix show us a better cover of malignant cases with 97 true positives. And although we'll still have 81 false positives, his trade-off is acceptable because our main priority is to avoid false negatives. That is, ensure that sick patients are not sent home misdiagnosed. Therefore, the combination of strong regularization and class balance provide the most reliable clinical balance of this study. This brings me to my conclusions and future works. Let me briefly recap the main points. Our initial hypothesis was the UNAT for detection. Under the conditions we evaluate, it was ineffective. The diagnosis was underfitting. With a training sample below 1,000 images, the network could not learn to delineate the exact borders of the lesions. For a deep learning task like this, that amount of data was too small, and the complexity of the task was higher than the capacity of the network to generalize. The classification with VGG16 works better. Even with a small data set, the transfer learning reached convergence in training. The validation results is modest but promising. The key methodological difference was, and our contribution here, was the strong regularization strategy with a dropout of 0.7. This was what reduced the overfitting and gave us a relevant diagnostic balance, with 66 sensitive in detecting malignant cases. This suggests that for this task, the global features may be enough. And one last point about time. In the test phase, the trained model classified a new image in about 3.2 seconds. This is the inference time, the time to give a benign or malignant answer for one new image. A speed like that matters for the clinical side. A system that reads a new image in few seconds could support the triage and public health system. For future works, we see three directions. First, the optimization of the architecture, testing vision transformers or efficient nets. The second, the evolution of the segmentation, more advanced versions of the UNAT, such as Attention UNAT or UNAT++. And the third, the clinical expansion, validates the transfer learning strategy on other diseases with high mortality that are diagnosed. That brings me to the end of this presentation, and I want to thank everyone for your attention, and I would be happy to answer any questions you may have.
Thank you, Flavia, for the presentation. Any question? Any question? No? Do we have questions?
No.
No? Any questions from the online participant? No? Okay. We're going to stop now. Give 2 minutes to start with Asrani.
Yeah, I'm here.
So the next speaker is Asrani Lit.
Yeah. A moment, yeah.
Just give some 2 minutes, Asrani. So I'm going to
Okay.
So
I think I cannot share my screen.
You cannot?
I think I need to. I cannot share my screen.
Try again.
can I rejoin? I log out first and I rejoin.
Right? Saiu. Saiu. Ele vai voltar. Now you're back.
Testing 1, 2, 3. Share the screen.
Yes, try. Okay, now we see again.
Okay.
Let me
For
just.
quick check, can you see my screen?
Yes, yes. Just wait a little bit. Asrani is from Malaysia. He's going to present a systematic literature review of network-on-chip architecture, topologies, routing, reliability, and emerging technology. All right. Now you can start, Asrani.
All right. Thank you, the chairpersons, and also hello to all the respected audience. Okay, my name is Asrani, and we are from Department of Electronics and Electrical Engineering, University of Malaysia, Sarawak. And the focus of my presentation is about systematic literature reviews of NOC architectures, which focusing on topologies, routings, reliability, and emerging technologies. All right. Basically, this is the outline of my presentation. So without further ado, I think I would like to begin with an introductions. As the increasing core count of the contemporary system on chip, or SoC, has been driven a fundamental shift from the shared bus architectures to the scalable on-chip interconnect networks, the NOC, or network chips, has emerged as the de facto algorithm for providing a high bandwidth, low latency, and energy efficient communication among the heterogeneous processing elements. Over the 2 decades of research, have produced a rich body of work on NOC topologies, the routing algorithms, flow control schemes, the quality of service or QoS mechanisms, the reliability enhancement, and the emerging technologies such as the wireless, optical, and 3D NOCs. Furthermore, these works present systematic literature reviews for NOC architectures, which ranging from 2002 to 2025, following transparent and reproducible methodologies. The basic NOC architectures. Basically, a typical NOC consists of a router interconnected via links in a chosen topologies. PE or processing elements such as CPU cores, accelerators, or memory controllers, it connects the NOC networks through network interfaces, whereas the packets are segmented into fleets and forwarded into across the router using a specific flow control scheme, which is often the wormhole switchings. Furthermore, the routing algorithm, it's determine the path and the packets that take from the source to destination, which subject to the constraints such as deadlock freedoms, minimum path length, as well as the congestion avoidance. All right. These figures shows a basic network on-chip architectures, which comprises the processing elements through the network interface, the router and physical links, which arrange in regular topologies such as to the mesh architectures. So the data communication is packet-based with router performing the routings, bufferings, and attribution functions to ensure that the efficient and scalable on-chip communications. And by leveraging the network principles, NOCs overcome the scalabilities and performance limitation of the traditional bus-based interconnects and have become a foundation communication for modern many core systems. The next presentation is about the methodology that has been carried out in these works. So the review protocols follows general guidelines such as the planning, conducting, the reporting, which illustrated in these figures. All right. These figures provide a high-level timeline of key development in NOC research. As can be seen in the figures, the early work focused on the regular 2D mesh and determinist robotics, whereas the subsequent periods introduced the topology variants and adaptive routing and QoS mechanisms. For the last decade has been a rapid growth in emerging technologies such as YNOC, ONOC, 3D NOC, as well as the machine learning assisted design, ML design. So to provide a structured overview of the research landscapes, these studies organize the existing NOC literatures into these taxonomies. And the taxonomies captures the major design dimensions, architectural considerations, and optimization objectives that have emerged over time in NOC research. So this figure present a taxonomy used in this review, which illustrating the hierarchical classification of studies across core architectural components, communication mechanisms, the system level requirement, and the imaging technologies. In addition, these taxonomies serve as a unifying frameworks for analyzing the trends, to identify the research gap, and comparing the representative works across the NOC domains. Next is on NOC topologies, where this table summarizes the representation of NOC, NOC topology and their key characteristics. As can be observed, the mesh remains the most prevalent due to its layout regularity and implementation strategies. The other variants such as torus, the flattened butterfly, and fat-free offer a reduced hop count as the cost of the increased wiring complexities. Whereas the 3D topologies, it exploit the through silicon bias or TSV to reduce the communication distance. All right, next is on NOC algorithms. The routing algorithm significantly influenced the NOC performance and its robustness. We group the routing algorithm into some categories such as the deterministic, partially adaptive, the fully adaptive, and fault-tolerant categories. And this table summarizes the representative of routing taxonomies. All right, this table summarizes the key characteristic of the emerging platforms. First is the wireless network on chip or WiNOX, where it uses on-chip millimeter wave transceivers to create a long-range shortcut that can reduce hop count and average latencies. Beside that, the optical NOC or ONOX, it leverages the silicon photonics and waveline division multiplexing to provide a high bandwidth, the low latencies, and 3D exploit TSV to stack multiple logic and memory layers. Last but not least, the ML-driven NOC use supervised and reinforcement learnings for traffic prediction, adaptive learning, and machine control and design space explorations. So my next presentation on the discussion for this paper. The first discussion is on the shift from regular to hybrid topologies. While the 2D mesh topology remains dominant in both academic prototype and commercials, the medical processor due its layout regularity and ease of implementations, the literature reveals that a gradual shift toward a more complex and hybrid NOC topologies. So, which means this include the architecture that has been augmented or improved with the express links, the hierarchical hubs, the wireless shortcut, or 3D stack vertical links, and also the photonic interconnects, which is to reduce the average hop counts and communication latencies. Such a hybrid design are particularly very intuitive for large scales and heterogeneous system where the communication localities and traffic ambulance are pronounced. All right. The next discussion is about from the deterministic to learning-based routings. The routing strategies in NOC has evolved from deterministics, like dimension order scheme, like expert routings, toward the adaptive and congestion-aware algorithms, which is capable of improving the throughput and fault tolerance under non-unific traffic condition, especially. And more recently, the machine learning-based routing approach have gained uh, rapid increasing attentions, which replacing the handcrafted heuristics and data-driven policies that learn from runtime traffic patterns and network states. However, several challenges hinder such widespread adoptions, and these include the hardware overhead, training stability, explainability, the routing decision, and formal verification of correctness and network freedoms. Next is on the focus on the reliability, energy, and thermal issues. With the continued technology scaling and increased integration densities, this issue have emerged as the first order design constraint in NOC architectures. These phenomena, such as process variation, aging, soft errors, and thermal hotspots, can significantly degrade the network performance and the lifetime of chips. Consequently, the recent studies have increasingly adopted cross-layer approaches, which Johnny considered as microarchitecture techniques, routing strategies, and system-level management policies. Therefore, this trend reflects a broader shift away from isolated optimizations toward the holistic NOC design frameworks that balance the performance, power, and reliability objectives simultaneously. The next discussion is on the evaluation methodologies and benchmarks. Previously, the simulation-based evaluation remained the dominant methodology for NOC research, which widely used NOC simulator, which including the BookSim, Garnet, or Germ5, and NoxSim. And most of these studies rely on synthetic traffic patterns, such as uniform, random transport, and hotspot traffic to stress test the network behaviors. However, as the NOC increasingly serve the communication backbone for the net accelerator and data flow architectures, recent work have emphasized that the need of benchmark traces that capture the multicast bursty synchronization heavy traffic patterns, which reflects with the characteristic of AI applications. In conclusion, this paper have presented a review of network architectures, which spanning more than 2 decades of research. And by using a structured protocol, we have synthesized some contribution across the topology design, the routing algorithms, flow control mechanism, OS support, the reliability and fault tolerance, energy and thermal aware techniques, emerging NOC technique, as well as ML driven NOC optimizations. In addition, we also provide taxonomies, comparative tables, and conceptual timelines that have highlight the evolution of the fields. Last but not least, the identify research gap and future direction, particularly in security, AI, central benchmarking, ML integration, and cross-technology co-design offer a roadmap for the next generation for NOC research and practice. So these are the main references that we have used in these works, and this is the rest of it. Which thank you very much for listening.
Thank you, Asrani, for the presentation. I have one
Welcome.
basic question for you. Maybe you can
Yeah.
help. I would like to understand, in the case of the adaptive routing, who's running the, for example, the network that is training to adapt the routing? Who's running the training and the execution in the network?
Okay, from my reading, I think it's from the routers. Router is the
But the router doesn't have any processing unit, does it?
from my reading, the router can be integrated with the processing unit. We can put, design the smarter routers in order to handle that.
Do you mean you have to add a processing unit inside the router, or is it the processing element that is attached to the router that is going to execute the algorithm?
We put it in the routers. Some kind of algorithms inside the routers. It can be done.
And do you think that it has computational power to do the computation online to help the routing of the messages? This kind of processor? Okay.
Yes.
Any question, Luisa? No? Any question? Juliana? Any question from the online participant? No. Azrani, thank you very much for the presentation.
Okay, welcome.
Thank you. Bye-bye.
Right.
Now, we have 4 minutes before the next presentation, so we're going to give it a rest a little bit. Is Vinicius here? Vinicius? He's here. Vinicius.
Yeah, good morning.
Good morning, Vinicius. It's Vinicius or Thiago?
Vinicius Thiago.
Vinicius Thiago, both of them. Okay. Vinicius, you are from Brazil, I guess?
Yes.
Can you share your first slide so I can present you?
Okay.
Please. From Rio de Janeiro as well, from the Military Institute of Engineering, IME. So Vinicius is with Ronaldo Salles, Julio César Duarte, and Gabriela Dias. All of them, they are from the Military Institute of Engineering, Rio de Janeiro, Brazil. He's going to present the work on 2D convolutional neural network-based link prediction in opportunistic network. This is new, opportunistic networks. let's learn something with Vinicius. We have three minutes before you start. Okay. Tell us about the weather there in Rio de Janeiro. Is it raining? Is it hot?
It's not too hot. It has rained the last week, but it's not raining now.
All right, and everybody is happy with the performance of the selection yesterday.
Yeah.
Not very, and very happy with the one from Germany, right?
Yes.
No one from Germany? No, France.
And from
France.
okay.
Yeah, today.
Okay, we wish you good luck. Okay, let's start. Vinicius Thiago, you have the floor for 15 minutes.
Thank you. And good morning. So our study is called 2D CNN-based link prediction in opportunistic network. So opportunistic networks, they are a subclass of delay-tolerant networks. which are networks in which the delay is acceptable in package delivery. End-to-end connectivity in an opportunistic network cannot be guaranteed. So communications occur in the absence of fixed infrastructure and relies on mobile nodes. They are equipped with short-range wireless interface, like Bluetooth. And in such environments, a direct path between source and destination is often unavailable. So the nodes depend on opportunistic encounters with other nodes to establish temporary link communications and enable packet forwarding. These characteristics give rise to the name opportunistic network, as the nodes keep waiting for opportunistic encounters to deliver the packages. To achieve the dissemination of messages, the nodes adopted a story, carry, and forward paradigm, in which the packets are temporarily stored in the nodes, and they are carried during node mobility, and they are forwarded only when a suitable contact opportunity becomes available. This operational model makes opportunistic networks particularly well suited for environments characterized by intermittent, sparse, or absent connectivity, such as disaster situations, battlefields, overloaded cellular network, and so on. The nodes operate under severe resource constraints, particularly with respect to energy supply and storage. So they must very carefully manage to prevent node depletion and the subsequent drop of the package. So a challenge in this network is the selection of the next hop nodes responsible for carrying a package. So designing forward strategies that maintain an adequate delivery ratio while avoiding excessive resource consumption remains a widely studied problem. Link prediction is a traditional problem in computer networks and to forecast future connections between two nodes. So based on characteristics observed in the networks, they try to predict future links. Accurate link prediction can significantly assist routing algorithms in selecting the most appropriate next hop node. So improved prediction may lead to more efficient forwarding. One approach to link prediction is the use of machine learning techniques. So this paper has two contributions. First of all, a two-dimensional convolution neural network is employed for link prediction on real-world opportunistic network datasets. The architecture was proposed in a previous work, Thiago et al. And in this case, the work is re-evaluated on a novel real-world opportunistic network dataset. The model's performance in a long-term prediction scenario is also evaluated on one real-world dataset, a scenario that was not addressed in previous work or related works. So, a link prediction in opportunistic networks. In this study, we choose to represent the network as adjacent matrix. So the trace of the network is divided in time slice, and we generate snapshot sequences. So we have a quantity of snapshot sequences that are used as input to the architecture, and the architecture predicts a number of future snapshots sequence. So in the picture, if we have a tau number of snapshot sequence as input, and the architecture could generate gamma predictors. So the link prediction task can be formulated as a binary classification problem applied to the entries of the adjacency matrix, where the value 1 indicates the presence of a link and the value 0 indicates its absence. There were previous works that used machine learning to evaluate link prediction in opportunistic network. It can be seen that a wide range of machine learning techniques has been employed in related work, such as LSTM, DBM, 3D convolution, transformer, graphical neural network, and so on. The AUC metric is the most commonly used to evaluate predictions, while PR-AUC is also widely adopted. Both metrics, they have the advantage that they are independent of the classification threshold, and PR-AUC metric is more suitable for high imbalanced data sets, which is the case in opportunistic network. From the data set that are used in the works, we can see that the ITC, MIT Reality, and Infocom 06 are the most used data sets. So many studies evaluated the models on a limited set of data sets. We thought that it was important to evaluate on the highest number of data sets. So it's not a particular solution. Existing works primarily focus only on short-term link prediction. We carried experiments in short-term link prediction and long-term link prediction. So we used 3 data sets: ITC, MIT Reality, Infocom 06. Both ITC and Infocom 06 use a device called iModes, which are equipped with Bluetooth interface. The ITC dataset presents 50 iModes and has a trace of 12 days of network. The Infocom 06 has 98 iModes and presents a trace that spans for 4 days. The MIT Reality, it's a trace made by mobile phones, also connected by Bluetooth. It presents 98 devices for a span of 282 days. So it's a much bigger data set. The 2D CNN architecture proposed in previous work consists of 3 intermediate convolution 2D layers, each followed by a dropout layer. The HC and MIT Reality datasets were partitioned into 300-second intervals The Infocom 06 was partitioned into 270 second intervals. These parameters were designed by a previous work, Shu et al. And all experiments were conducted using an input sequence of 10 adjacent matrices. So these were the results of single matrix prediction with an input of 10 matrix and a prediction of one future matrix. Comparing the results with the previous works, it can be seen that the AUC metric is particularly good for all the data sets. And the PR AUC metric was the highest in the MIT dataset. And it is very competitive in the other two datasets, ITC and Infocom, with an attention to the Infocom 06 dataset, the work of Zhang et al. Obtained a 0.96 PR AUC, which is very, very high. And the work uses contrastive learning. So it's a much more computational expensive solution, but it was a remarkable result. Talking about single predictive matrix, they cannot provide sufficient information to effectively support forwarding decisions. So we thought it was desirable to forecast links over extended time horizons and chose to perform multiple matrix prediction. Due to the limitations of the traces during the days of the ITC and Infocom 06 datasets, the MIT reality mining was selected for the experiments using multiple matrix predictions. We use a subset of 10 days of the dataset, and the model was provided with an input sequence of 10 adjacent matrices and tasking with prediction 10 consecutive future matrices. So these were the results that were obtained, the mean results. We can see that both metrics exhibit a gradual decline as prediction extends further in the future, with PR AUC dropping much more fast than AUC as we go further into the future. But it's important to notice that the baseline for AUC is 0.5, which they expected of a random classifier. And the baseline for PR AUC is determined by the prevalence of the positive class, which in the subset of MIT reality use is 0.0014, which is much lower than the results obtained, even in the 10th predictive matrix. So the 2D CNN model achieved superior performance, particularly on the Infocom 06 and MIT reality mining datasets. Although multi-step prediction results show a gradual decline in performance, results remain significantly above the baseline values. And this finding suggests that long-term link prediction opportunistic network. These capabilities may support more effective forwarding decisions in routing protocols, potentially improving network efficiency. So the model effectively predicts future network connections, and deep learning-based approach represents a promising direction for improving link prediction, supporting routing structures. As suggestion for future work, we can conduct sensitivity analysis on the 2D CNN architecture with respect to key parameters, like the extent of the snapshots and the number of input and output sequences. We can adapt the current model to more advanced deep learning architecture, such as graph neural network and temporal graph network, to verify how it will affect link prediction and the associated training costs. We should explore online or continual learning strategies, enabling the model to dynamically adapt to evolving network conditions over time. And I think the most important is to investigate the use of bootstrap future adjacent matrix prediction in message forwarding protocols. So this proposed protocol could be evaluated in a simulation environment using the MIT reality mining dataset, allowing its effectiveness to be assessed under realistic network conditions. Thank you very much for your attention.
Thank you, Vinicius, for the presentation. Very nice presentation and perfect timing for a military person. Let me just, any question? No? Let me just ask you, did you do the simulation or did you do the experimenting with the mobile phones and iModels?
No. These data sets they are public domain. They are in IEEE, and we only use the trace for a future test with the forwarding protocol. We are using the data sets in a simulation environment. It's called ONE. It's opportunist network environment, and it uses the trace to perform a simulation network.
So now you made a program that use the data set and get the metrics, right?
Yes.
So your next step would be the simulation on some platform that simulates the opportunistic network.
Yes, and a forwarding package protocol.
Yes, and then the third step would be experimenting on the real devices.
Yes.
What happens if the one of the devices, the nodes, go offline in this kind
So
of?
it happens all the time in this kind of network, and when he goes offline, all the packets that are within it got lost. So there are some strategies to forwarding, like multiple copies and such. But if we use too much copies, we deploy energy in the same way. So that's the key component of the forwarding strategy, is to choose the best nodes, and with some how can I say, some plan B if this first forwarding isn't successful due to node depletion.
Right. Thank you very much for the explanation. Okay, we can call it off. All right. Thank you very much.
Thank you.
Thank you. Now we have another presentation, and we have time for rest, a little bit of rest, 2 minutes. Cristiano Alex Unas is here. Daniel, no, Gabriel.
I will present this work.
This is, what's your name?
I am Thiago Araújo, one of the authors.
Oh, Thiago Araújo. And one of your co-author is Philippe Navot?
Yeah.
From Rio Grande do Sul, right?
Yeah.
All right. polyglot. So you're going to present characterizing lossless GPU data compression across AMD, CDN, and RDNA architecture. Can you tell us what the CDNA and RDNA architecture are? What's this, the abbreviation?
It's different kind of GPUs. CDNA is the GPU that are used in high performance clusters, and RDNA are more gaming GPUs, more customer GPUs. So this is the main difference.
So the
I
C is,
don't know.
all right, the C is cluster and R is?
I don't remember.
You should
I
know.
don't remember exactly.
Okay, now Thiago, so you're going to present, you're from Porto Alegre, Fevers, and you are also with Lawrence Berkeley, you're doing your PhD there, you are in the state now? Presenting
No,
for
no. It's a collaboration, and Cristiano is doing a PhD, and his research is in partnership with Lawrence Berkeley National Lab, with Gianluca Bess. There is a professor. He, he also research in Berkeley. Yes, they
So
are
you are
collaborating together.
supervisor of Cristiano,
Yes.
the supervisors, right?
Yeah.
All right, okay. Okay, now you have the floor to start your presentation.
Okay, and good morning, everyone. My name is Thiago, and today I'm presenting this paper. The central idea is to understand how data compressions behaves on AMD GPUs, which today power some of the largest supercomputers in the world. And this is our roadmap. I will start showing some introduction and the motivation of this work. Then I will give some background about AMD GPUs and compression. Then I'll speak about the tooling gap between NVIDIA and AMD. Then I showed our methodology, results, and conclusions in future works. So the underlying problem is simple. The volume of simulation data grows faster than our ability to store or move it. Workloads like seismic, climate, and fluid dynamics generate gigabytes to petabytes per run, and the bottleneck is no longer computation, it's data movement. This is what we call the I/O wall. And the figure shows exactly that. Data lives in the cluster and PDM targets this wall with only a trick getting through. GPU accelerated compression emerged as a way out because it can reach throughputs above storage bandwidth, and it's already in use in HPC to cut both capacity and transfer costs. But there's are imbalance on the NVIDIA side. There's NVComp, a metric library, vendor-supported since 2020, with tunneled implementations of several algorithms and seamless integration to CUDA workflows. On the AMD side, the picture is different. AMD GPUs power El Capitan and Frontier, the top two of top 50 100. The latest list from June changed this, but the equivalent to HipComp is still experimental and covers few algorithmics. Practice, people working on AMD GPU must part the code themselves, use optimal tools, or forgo GPU's compression altogether. It's this gap that our work addresses. So our contributions has three fronts. First, characterize and measure lossless GPU compression across several AMD generations. Second part, with functional CUDA to heap part of three algorithms as Z4, Snappy, and Cascaded from NVCom 2.2, establishing an open baseline for AMD, and finally analyze, that is, understand how cache, memory, bandwidth, and wavefront behavior shape performance across CDNA and RDNA. So to understand the results, you need to know AMD 2 GPU families. CDNA is aimed at data centers and HPC, a focus on high throughput and high bandwidth memory, 8BM. It involves from the MI50 to the MI 210, and the MI 300X. The MI 300X is the flagship we had access, 300 for computer units, 192 gigabytes of 8BM3 over 5 terabytes per second of bandwidth. RDNA is the consumer game line, but it shows up cost-sensitive HPC. It has a complicated design and imported for us a 96 megabyte infinite cache and higher clocks. The representative here is with RX 7900 XT, and the point that applies it all together, Hakama and HIP allows portable code across AMD and NVIDIA with minimal changes. That's make the part. This table summarizes the four GPUs evaluated. The thing to fix in your mind is the range they cover. The MI50 is our baseline. The MI300X represents the very high bandwidth extreme at 5.3 gigabytes per second, and the RX 7900 XT represents the consumer extreme, cache rich but with much lower bandwidth, 800 gigabytes per second on GDDR6. So about the port itself, the base is NVComp's matched API, which possess when independent data chunks in parallel with maps natural onto heap model. There are three phases. The first one was API translation. The heap file perf to handle about 90% automatically. The manual work was swapping cube to heap cube and adapting the warm primitives. Build adaptation CMake now targets the GFX identifiers of each architecture with an option to compile for 32 or 64 threads wavefronts. And correctness validation, we verify that the compressed data returns the original bit for bit across all chunk size types. For evaluation, we built four data categories along the compression spectrum, as the figure at the bottom shows. Zeros, which compresses maximally, binary with 70% repetition, random, compressive, and TTI, real seismic data flow. The TTI comes from a real RTM run of 500, 448 qubit width, 201 time steps, and 57 gigabytes. It's our actual use case, and we measure from a midpoint to avoid inflation the rate due to the initial value being zero. Each dataset was tested at four size, from 10 megabytes to 4 gigabytes. We run 3 warm-ups and 10 timed repetitions with throughput measure via heap event, isolating the kernel, and everything is in singularity containers on grid 500, 5000, and use PCAT infrastructure to ensure reproducibility. So here's the beginning of our results. This chart has compression throughput on the top and the compression on the bottom for the four GPUs and the three algorithms. Four things to note. Data compressibility dominates LZ4, LZ4. On the MI300X, it goes from 840 gigabytes per second on zeros to just 15 gigabytes on seismic, more than 5 times, 15 times difference. Cascaded is stable because its pipeline is fixed and independent on the context. And the thing to note is that compression, the consumer RX 7900 XT does very well thanks to the infinity cache. And finally, in the compression, the MI 300X dominates, driven by the 8BM3 bandwidth. That contrast catch helps compression, bandwidth helps the compression, is a thread running through the oil work. So, but the kernel throughput doesn't tell the oil story when you include transfer between CPU and GPU, the picture changes. This chart breaks total time into four phase, transferring compression, the compression and transfer out for the same data, and the transfer dominates on average on the MI300X with very fast kernels as before compression drops to about 13% of the total. On the RX 7900 XT, cascaded falls below 5%. The practical conclusion is direct. Optimizing the kernel alone gives this machine return, while the transfer dominates. The real gain appears when compression happens with the data already resident on the GPU. For example, compression the simulation output before writing the task. And here we have the compression rate. The table shows the three algorithms across the four data types. And note that these numbers are independent of the GPU. They depend only on the algorithmic and the content. The highlight in red is the seismic data, 1.03 to 1.04 times. That is almost nothing. And the three algorithms land in practically the same place, which shows that seismic data in Flow 22 has very little bit level redundance for lossless compression to exploit. The message is the right-hand panel, the K1 for this kind of data. Lossless compression is a baseline, not a reduction problem. And that is precisely what motivates the error-bounded lossy path, ZFP and SZ, which appears in future works. So the idea is to explore these other algorithms that has lossy. And in here we have the generation gain relative to the MI5050 our baseline. This one for compression, the MI300X reach 8 times for snapping and cascading on larger inputs, as for gains less, up to 6 times because it's limited by hash table latency and that doesn't scale with bandwidth. And finally, the RX 7900 XT is consistent up to 4 times across all algorithms and size, supported by the cache and the hyperloop. And the MI 110 shows moderate gains up to 1.7 times. And here's the compression, where the gain is larger. The MI 300X reach 11 times over the MI 50, as if for a snap bandwidth loss on the 8BM3 bandwidth. The RX 7900 XT is more modest, up to 3 times, limited by the 800 gigabytes per second GDDR 6, and the MI 210 scales with bandwidth up to 22.4 times Drake's 1.6 bandwidth advantage. And the final takeaway is that asymmetric decompression wants raw 8 bm bandwidth, compression wants cache. This means the hardware choice depends on which phase dominates your workload. So if the compression dominates, you need to more cache, and if you are decompression, you need more bandwidth. So as our conclusions, to wrap the conclusions first, there are clear architectural asymmetry. RDNA3 is competitive for compression, while CDNA3 dominates the compressions up to 11 times the MI15. Second, PC Express transfer dominates end-to-end times, so the gains appears in workflows where the data already lives on the GPU. And thirdly, on real seismical data, lossless yield only 1.03 to 1.04x. It's a baseline, not the actual reduction. And finally, we deliver an open CUDA to part that establish a foundation for future AMD specific optimization. And as our future works, CDNA optimized kernels using the full 64 threads waveforms and moving the hash table into the LDS, the fast local memory, data per condition byte shuffle to char to expose redundance that escape general purpose compressions and integration of error bonus loss decompression, ZFP and SZ, which typically reach 10 or to 100 times on similar data. Then you find an API that compiles from both factors. And our acknowledgements, we acknowledge the support of Petrobras, CNPq, and CAPES, the U.S. Department of Energy, BLBNL, and the PCAD and Grid 5000 infrastructure where experiment run. And that's it. Thank you for your attention.
Thank you, Thiago, for the presentation. Uh, any question? No? No? Let me see. You didn't propose any algorithm. You used some algorithm that exists, and you compared their performance on these two specific GPU architecture. Is it right?
Yes, yes. The main idea is to create a tool in the AMD uh, GPU for AMD GPUs that are not any other tool library with maturity and with many algorithms. So the idea is to use NVComp and port it to from the NVIDIA infrastructure to AMD and create this tool. It's a gap that we found when we are trying to make compression, decompression in the Petrobras project that we work. So this is the main idea. It's create this library. So here we have we characterize and we make the part, we analyze, but we not optimize. So this is one of our future works that we want to do because our current results are not really good in the AMD, are not optimized. So that's the idea.
But what is the motivation behind selecting these two specific GPU architecture? Do you know?
Okay, so AMD is used in the largest supercomputers in the world. The first and the second highest supercomputer are using a GPU AMD GPU. So this is the motivation. And NVIDIA is not anymore used in the highest supercomputing. So if we run experiments in this biggest supercomputers, we want some tool that made the compression more quickly and something more with more maturity. So this is the idea to develop this library. It's initial work. There are a lot of things to do, but our idea is to have something similar with NVComp, a really mature library that exists in NVIDIA uh, behavior in AMD. So the motivation is because a lot of new supercomputing are using AMD GPUs.
And is the results and your work available publicly, or is it just for you on your project?
Yes, it's public. We have the idea is I think in the paper there are the GitHub with the tool and the results and everything. I don't know exactly if everything is public for now because we are doing some adjustments in the repository to make everything public. But the idea is everything public and everyone can use this tool and see the results that we archive.
Okay, thank you very much, Thiago, and success. Wish you success for the project of Petrobras. Thank you. Thank you. And this closes our session on time.
Yeah.
Okay.
Exactly.
We go to
Right in time.
I made conversation and tell the time. Okay, then we go to the coffee break, right?
Yes.
Okay.
You know where is the keynote student?
I don't know, maybe it's downstairs. Let me see in the problem. No?
I
Should be, it should be.
the large
Reception. I don't know by head, no, I say. Yes,
the teacher of the.
it should be there. Yeah, there is no detail about the room.
Maybe on the room.
Yes, a decline, but I don't know where it is.
It's in the
Downstairs?
ground. Yes.
Let's go there, let's go. Some coffee,
Yeah.
not to sleep in the
Close the main entrance.
para não dormir.
Sim.
The main entrance is the room, I guess.
Thank you, Juliana, for and sorry, I thought there is não tem nenhuma etiqueta ali dizendo isso aqui para luz, isso aqui para
Pois é. Falharam mesmo.
Mas foi assim, menos mal.
Uhum.